So let me start with a story. Actually, I'm going to get you back to 2000, and this is the first year that I was teaching as a primary school teacher. And back then, based using all the ideas that I got from the university, I started teaching my fourth graders, and I was using all these representations and manipulatives, expecting that students would simply get the mathematical ideas. And of course, some students were getting the mathematical ideas, others were struggling, and still others were confused. Um, and back then, I'm realizing right now, I was putting all my magical hopes into these representations and manipulatives, thinking that they would work. And these magical hopes were soon dashed. And today, I would like to use this opportunity and talk about how we can turn these magical hopes into realistic expectations, how we can use representations and manipulatives to really foster students' mathematical understanding. And having been a teacher, a practitioner on my own, I'll try to keep the theory to the minimum, and I will try to give particular examples about these ideas. So without further ado, let us get started. So these are pictures of representations, and I'm sure that you will be recognizing at least one of them. You might be using at least one of them in your practice, because representations and manipulatives are actually a very central teaching aid. And we know from the literature that they are supposed to be supporting student learning, but oftentimes they are not. So why is this the case? I'm going to refer to a very nice paper. It was written back in 1992, but I strongly recommend that you have a look at it. It was written by Deborah Ball, one of the renowned mathematics educators in the US. It's called Magical Hopes, Manipulatives, and the Reform of Math Education. And in that paper, Professor Ball is using the analogy of the mathematical bicycles. And she's referring to the training wheels of these bicycles. And actually, she parallels manipulatives to these training wheels. So oftentimes as teachers, we're introducing all these manipulatives, and we're hoping that they're going to be acting as training wheels. But to our dismay, when these training wheels are removed, the students cannot really write their mathematical bicycles. Then the problems start. So students revert to using the algorithms mindlessly. They have problems with the mathematical ideas. And it seems that these training wheels do not work. And actually, Deborah Ball is talking about these the magical hopes I was referring to. So why is this the case? In this presentation today, I'm going to answer this question by actually considering three related questions. First, why are we using representations and manipulatives? And in order to answer this question, I'm going to be referring to what representations and manipulatives actually are. Then I'm going to address a second question. What representations and manipulatives should we be using in different situations? And the real question is, does it really matter if we pick the one or the other? And finally, I'm going to conclude with a third question, how we should be using these devices to ensure that when these training wheels, to use Deborah Ball's words, are removed from our students' bicycles, students can still ride smoothly and confidently. Okay, let's start with the first question. What representations and manipulatives are? And in order to define this, we need to be referring and we need to be making a distinction between external representations and internal representations. External representations are the pictures that I've just shown to you. And you can see them here as well. Bortin and Polik are using a nice definition. It could be a sign, a configuration of signs, characters, or objects. And the most important thing is that they can stand for, they can symbolize, they can depict, they can encode something other than itself. An idea that is also mentioned by Duval. These are entities that symbolize or stand for other entities. And I'm going to be using the term representation from now on to referring to the external representations and the manipulatives collective. So in essence, we're using these external representations, hoping that they are going to reinforce students' understanding, hoping that they're going to shape students' internal representations. So internal representations are actually the things that go on in students' minds, how ideas get organized in students' brain. And Dean and colleague again are talking about how the different notions are organized in the brain, how they get symbolized, but they also talk about natural language, the visual imagery, spatial representation, problem-solving strategies and heuristics, and even affect, how students think about themselves in relation to mathematics. And we have just heard from the dean that by grade 8 she has internalized this idea that solving mathematics and doing mathematics was really hard. So that was part of the internal actual representation that she was kind of forced by her teachers to make. So again, the idea is that we're using external representations in order to support students' understanding of internal representations. And actually, that's the first affordance of using representations. We are thinking that by using these representations, we're going to help our students connect the mathematical ideas to different procedures, to different concepts, to different strategies. And we hope that all these abstract mathematical ideas and concepts are going to be made accessible and visible to the students. But at the same time, we're using representations because they provide a window to us as teachers in order to understand how our students are thinking about mathematical ideas. In essence, they provide a window for us to their thinking, to their brains, because we're making inferences about how students get to understand different mathematical ideas. But there's also another reason that representations actually provide for us, teachers and students, a tool and a language code through which we can communicate important mathematical ideas. But nothing comes without its price. So there are certain challenges when we use representations. As Deborah Ball was referring to these training wheels before, the truth is that oftentimes our students know and they imitate certain procedures. They know how to carry out the procedures, but when it comes to their conceptual understanding, we see that this is problematic. It's again this analogy of removing the training wheels and students follow their mathematical bicycles. There's also there's also another challenge when we use representations as if they are ends in themselves. And if I were to go back to the 2000s, I was doing this myself, and I was doing this a lot because back then a certain representation was introduced in our mathematics textbooks, and I was forcing out my students to learn how to use this representation to solve mathematical problems, whereas the students did not really need it. So I was treating this representation as an end in itself instead of treating it as a means to reinforce students' understanding. But there's also another paradox. We're thinking because we know the mathematical concepts and we are adults and we have learned them through many years in schools, we think that they are very transparent to our students, and we think that simply by using representations, these representations by default are going to work, and that they are going to illuminate these mathematical ideas, which is not the case. Students do not necessarily see what we are seeing when we use representations. And about 20 years ago, the National Council of Teachers of Mathematics in the States has really emphasized a lot that it's not simply by using representations that we will get our students to understand the mathematical ideas. We have to expose them to different representations. We have to ask them to use multiple representations and move from the one to the other in order to start developing understanding. The Mathematics Methods Planning Group at the University of Michigan, of which I was a part back in 2008, has summarized all these challenges in 4 points, in 3 points actually, while adding another one. So they refer to creating parallel worlds. So we have representations on the one hand, we have the mathematical symbols on the other hand, and these are not really connected. And we're going to consider a couple of examples today to show how these two parallel worlds can actually come together. Other times we're using representations as though they are the ultimate learning goal, which is not and should not be the case. And by using representation, we might end up creating mathematical jargon for parents and students, which can obscure the communication. And all of us who have been using these representations know very well that the use of representations can also create a lot of management problems, especially when we're teaching young students. Kids want to play with these materials that we're providing them, and they do not necessarily think of them as mathematical tools. So these are all the challenges, or at least there are some of the challenges that we face when using representations. So teaching with representations is really hard. And for teachers who have been using these representations, they know this very well. In fact, in 2014, with a group of colleagues at the Harvard Graduate School of Education, we published a paper, and we tried to decompose what is involved, what is entailed in teaching with representations. And we came up with a long list. And again, this list is not exhaustive, it's not meant to be exhaustive, it's indicative of the different tasks that are involved in teaching with representations. And we developed this list by actually studying lessons in which teachers were using representations. It will take many hours to unpack all these different tasks. So today I'm going to be focusing on just it. So I'll be talking about the importance of selecting representations, how important it is to carefully select the representations that we're using. And I'll also be talking about the importance of using appropriate language and notation when using representations, and how we can use one representation to help students make sense of another. So I'll be using just 3 of these tasks in the rest of this presentation. So having talked about the first question, what representations are and what their affordances and limitations are, let's shift to the second question. What representations should we be using, and does it really matter? And in order to answer this question, I'm going to be presenting 3 different teaching scenarios. I know that we have people attending from grade 1 till grade 9, if I'm not mistaken. So I have prepared 3 different teaching scenarios for different grades. So if you're a lower elementary school teacher, imagine that you're teaching subtraction of whole numbers. Imagine that you are teaching 72 minus 35. Which of the following representation should you be using, and why? Are you going to use money? Are you going to use the Dean's blocks? Are you going to use the bundles of sticks, or are you going to be using Unifix cubes? And I'll be sharing this slide again, but let me move to the second scenario. If you're an upper elementary school teacher and you're teaching addition of fractions with similar denominator, which representation are you going to use? Circles, eyes, the pizza model? Are you going to use rectangles? Are you going to use pattern blocks? Or should you be using the number line? And then moving to the third scenario, if you are a middle grade school teacher and you're teaching integer subtraction, which representation are you going to be using? The number line, color chips, money, which you can use as assets and debt, or the thermometer. So I'm going to be giving you actually 2 minutes, and I want each of you to think about the affordances and the limitations of these representations. That's really important in order to make sense of what we're going to be discussing in a while. So you have 2 minutes, and use these 2 minutes to think about the different representations. Okay, so had this been more interactive, I would have taken some answers, but unfortunately, given that this is mostly a lecture, I will do the talking, and hopefully some of the things that I'll be mentioning next are going to resonate with some of the thoughts that you had during these 2 past minutes. So what I asked you to do actually was not to go into depth regarding each of these representations, but to simply start thinking about their affordances and limitations, because it does matter when it comes to deciding which representation we're going to be using. It really matters, and we're going to see this when we're going to be considering the examples in the third part of this presentation. The important thing to keep in mind is that we do not have representations that are inherently good or bad. It depends on the purposes for which we're going to be using the representations. So this is what we're going to be doing in each of the 3 scenarios that I shared. So for the first scenario, the subtraction of whole numbers, you had to consider whether you would use money, Dean's blocks, the bundles of sticks, and Unifix cubes. And let me start with the affordances and the limitations of these representations. First, I'm going to start with familiarity, because this is important. It's important to take into consideration whether certain representations are more familiar to students or not. So definitely money is a familiar representation to students, and bundles of sticks could also be, whereas the Dean's blocks and the Unifix cubes, at least at the beginning, they are not. But at the same time, whereas money is really a familiar model to students, it has a limitation. It does not preserve this idea of the proportionality to size. And what do I mean by that? So if I take a $10 note, that is not 10 times bigger as a single dollar. this is not preserved, whereas in the other three representations, this is the case. And this is important to keep in mind because oftentimes when we're using these representations, such limitations can block students' understanding. We also need to be thinking about what type of a model these representations are. So if we're referring to money and the Dean's blocks, we need to keep in mind that we cannot break them apart. So when we're using these representations, we need to be talking about trading one unit with another unit. And I'll be doing this in the examples later on. So keep this in mind. Whereas if we're referring to bundles of sticks and unifix cubes, these are groupable models. So we can bundle and unbundle the bundles of sticks. We can join the unifix cubes and we can break them apart. So we can use this type of language. But there are also other logistics that we need to be thinking. So for example, of course, paper money is less expensive as compared to Dean's blocks. But at the same time, this idea of the one-tennis, the relationship that I mentioned before, is preserved only in the latter three representations. We also need to be thinking about the numbers that we can represent. We can represent large numbers with Dean's blocks, large numbers with money, whereas with bundles of sticks, it can become really cumbersome trying to accumulate all these bundles of sticks together. And also when we use Dean's blocks, if we redefine the unit, we can easily shift to operations with decimals. So we can say that, you know, a flat, for example, becomes the unit. So then we have, you know, the tenths and the hundredths. That was, you know, a brief summary about some of the ideas that you might have thought with respect to the first scenario. Moving to the second scenario, that of adding fractions, and you had to consider four different representations: the pies, the pizzas, which we often use, rectangles, the pattern blocks, and number lines. And again, I'm starting with familiarity. Yes, pizzas and rectangles might be really familiar to students. Pattern blocks and number lines, at least initially, they might not be. The good thing with pies and rectangles is that we don't have any restrictions in representing fractions as we have with pattern blocks, because with pattern blocks we can only represent certain fractions. But at the same time, we need to be considering the ease in partitioning these models. So for example, pies are really hard to partition if we're talking about fractions like 1/7 or 1/9. For those of us who have asked our students to do that, it's really hard. And then, you know, of course, you know, students might be drawing pieces that are not equal, and they might say, okay, just pretend that they are equal. We can avoid this complexity by using rectangles. Rectangles are easier to partition when it comes to those more difficult fractions. But at the same time, if we want to reinforce the idea that a fraction is not only the relationship between the part and the whole, but it's also a number, then we can use number lines. Because number lines actually capture both concepts. We can be considering fractions as through a part to whole notion, but we can also be considering them as a number. That's the measurement interpretation of fractions. That is, in a nutshell, you know, some of the considerations regarding the second scenario. And right now, moving to the third scenario, that of subtracting integers, and we're going to see an example of that later on. We could be using number lines. We could be using the color chips, that is, chips of different colors to represent the positive and the negatives. We could be using money or a thermometer. And money are, of course, as I mentioned before, more familiar to students compared to the other models. But it becomes really complex when we want to teach integer subtraction with money. So if I ask you to pose a problem for integer subtraction using money, that would be really hard. I've listed an example there, so I tried to list an example, and as you can see, it doesn't really work. So the problem is, I have $5 in my piggy bank. My father decided to strike the $3 debt that I owe him. How much money do I have? Well, I still have $5. That's not 8, which is the answer that I could be expecting. Same thing with the thermometer. So I cannot pose a problem that really represents in an authentic way this subtraction. So I cannot say, for example, yesterday it was 5 degrees Celsius, and today the temperature has decreased per -3. I don't say this. It has decreased per 3 degrees Celsius. So money and thermometer could be closer to students in terms of familiarity, but they're really hard when it comes to using them to talk about integer subtraction. Color chips are better in this sense because I could say that if I have, let's say, a blue and a red chip, they cancel each other out. But I need to emphasize a lot this idea of additive inverse. And at the same time, I need to keep in mind that cardinality, which is how many chips I might have on the table, is not the same as their value. And I need to be doing some work around this. And as you will see in the example during the third part of the presentation, I'll be talking about this distinction, trying to help, let's say, students to get this point. Number lines could also work, but number lines could be difficult in the sense that they have a lot of rules that students need to understand. So, for example, if I want to have the subtraction 5 minus 3, so then I need to tell my students that I stand at 5, and then I need to turn backwards in order to represent the negative sign, and then I need to be moving backwards in order to illustrate the subtraction. So there are a lot of rules involved in using the number line, and it could confuse students. So these are some of the this is the thinking, or at least some of the thinking that needs to go when we think about using different representations. And the bottom line is that it matters which representation we're going to be using. It matters for the language that we're going to be using. It matters for how we're going to be using this representation in order to avoid certain to avoid creating certain misconceptions to students. With that said, let's turn to the third question. How should we be using these representations in order to ensure that when these training wheels are removed, our students can still ride their mathematical bicycles smoothly and efficiently? So I'm going to argue, and I'm arguing this along with several other scholars in mathematics education, that we need to be following some basic principles. First, the importance about linking different representations. And in the examples that we're going to be watching in a while, you will see that the teachers are trying to link their representations to the mathematical symbols, to the mathematical ideas, because otherwise we're creating parallel worlds for our students. Then there's also another principle, the principle of using mathematical language with accuracy. So certain representations go with certain mathematical language. So we cannot be talking about, breaking Dean's blocks apart, because you simply cannot break them. You need to trade. A third principle has to do with highlighting key mathematical ideas. We're using the representations, but at the same time, we need to be highlighting key mathematical ideas. And finally, we can use the representations as a means to foster multiple solution approaches and show to students how this could be done. In order to help you understand these 4 principles, I have prepared 7 examples starting from lower grades and ending up with upper, the grades, grade 8, grade 9. And I'm going to be using different representations each time. So we're going to be discussing subtraction of whole numbers, multiplication, division, and then shifting to fractions. We're going to be discussing multiplication and division, subtraction of integers, and we're going to be concluding with solving a problem using a particular representation. So let's start with subtraction of whole numbers. And let's assume that we want to subtract 302 minus 178. And I'm going to show a clip where the teacher is actually